How does a modern aircraft imitate nature? The comb at the front edge of an owl's wing generates vortices that modify the flow on the top of the wing, allowing them to manoeuvre at extreme angles. The same concept is used on modern aircraft, where vortex generators, these small protrusions, are often used on the top surface of wings. In 1987, the Stars and Stripes boat won the America's Cup with what was then a revolutionary surface that imitates a shark skin. These riblets have now been implemented on swimsuits for competitive swimming and on some advanced aircraft. Shark skins have tiny grooves aligned with the flow of water around the shark body. These are the riblets. They have been shown to reduce the friction between the shark skin and the surrounding water, making it possible for the shark to swim faster and with less effort. There is more to nature than meets the eye. We're inspired by living organisms, trees, birds, fish and reptiles, and we use these to find solutions to some of today's engineering challenges. The energy crisis back in the 70s increased awareness of the importance of green technology, and now there are concerns about minimising the impact of travel by reducing CO2 emissions from airplanes, cars and other forms of travel. The Flow Control Research Group at Imperial College London and our partners IMFT and the LAPLACE labs in Toulouse are looking for innovative solutions to some of today's challenges in making more energy efficient machines. We look for inspiration from nature, but nature has many other constraints such as survivability and reproduction. So nature does not always present the optimal solution for one objective such as energy efficiency.
We're looking at ways to reduce the friction between a surface and a fluid flowing over it. And if you look at an eel, when they're swimming along, they have this large wavy motion. They use that for propelling themselves. But if you look more closely, you can see there's a shimmer in the skin. And we're able to replicate that. And what we've done is we have fabricated lattices which can shake in plane and give hopefully the same reduction that the eels see. If an aeroplane is flying along and it tips its nose up, what can happen is that the flow over the wing can become detached from the surface, and this causes the aircraft to plummet. And if you look at some bats, they have muscles in the middle of their wings which allow them to change the stiffness locally. And we're able to replicate that in the laboratory, and we're producing wing models that can bump in a controlled way for exactly the same reason.
Scientists at IMFT and the LAPLACE labs in Toulouse have been working on methods to modify the wing profile and make it aerodynamically efficient. This requires large deformations that are typically required only a few times during flight, such as at takeoff and landing. Currently, this is achieved through complicated movements of rigid parts on the wing. Here, morphing of a semi-rigid wing is achieved through forces applied using a material called shape memory alloy, which deforms under the application of an electric voltage. Noise and drag can be reduced by the active control of turbulence. This is done by vibrating the rear edge of the wing. The characteristics of the wake, the region behind the wing, are altered by the vibration. The intensity of the turbulent structures in the wake is reduced so that drag is reduced. This improves fuel efficiency and reduces the noise too. Other techniques for reducing turbulent drag, noise and fuel consumption have been inspired by studies of the wings of a pelican. Electrically controlled feathers resembling those on a pelican's wings and made from a new generation of polymers are now under development. If you'd like to see some of these experiments in action and for a hands-on explanation, please visit us at the Royal Society Summer Science Exhibition at the beginning of July.